viewers. Come on, viewers. Come to me. Show this. Yeah. I'm a bit short of cameras today. Yeah, and what about sound? Sound, do we have a sound? Browser is not working, but this one is okay. Yeah, it's okay. I have a network. 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 What's in my network? One three-phase transformer. Three. What? Oh, 300 watt. One capacitor box. And pair of switches. I have a switch block here. I can choose one capacitor, and I have this neutral switch. I know this is connected to three-phase network. At this moment, it's connected like this. This one disconnected, this one connected. 3 amps. Switch. 1, 2, 3. 1, 2, 3. Now question, what will happen if I disconnect this little switch? At this moment, it's connected. What will happen if I disconnect it? Somebody told me what you all passed electrotechnics theory. So, your idea what will happen? If I disconnect it, what will happen?
Nothing will happen. Same. Okay.
It's from some old 1957 medical equipment. It's a patient treatment timer.
Oh. Stop what?
Apply voltage. Answer. Stops. Needs servicing. Okay, so what will happen? Any idea?
Nothing will happen.
Nothing.
Same.
And nothing happens. Okay, I'm changing valve to capacitor. What will happen? Oh, you see current flows. Maybe I can increase it. What will happen? Now it's capacitor instead of valve.
Oh, now you see change. What
I've disconnected this switch and I've connected this switch. What will happen?
Nothing will happen again.
Oops.
Oh.
Current.
Magic. Oh,
I reduced capacity twice. Nothing? No. First version, nothing happens. Second,
Power transfer.
see, not so easy, yeah. But that's not all. What will happen if I disconnect? How do you think? What will happen if I disconnect this wire?
Which wire? Oh.
This ground wire connected. Ground wire disconnected. Can do the same with phase C. This is all very strange. Little change. It's quite a complicated thing, isn't it?
Yes.
But we need it. Why we are so interested in polyphase network, in three-phase network? You know why? Only once. Very small. I destroyed. Why?
Magnetic.
Polyphase network. It's often drawn like this: A, B, C.
No, no.
not the best. A, B, C phase voltages. Shift between them 120 degree or 230 radians. If you apply such voltage to the system of one coil, second coil, third coil, what will be result? If this will be A, B, C coil, you will get a rotating magnetic field. Put something conductive inside it, and current will be induced, and when current flows, magnetic field arrives. So you will get below a synchronous machine, cheap and reliable way to drive something. It's cheap and reliable machine. This way. And free. Why three phase? First attempts were made with two phase systems. Two phase, two phase, two phase. Two phase motors looks like this. It's two phase. One, two, 4 wires. The steel in United States can be found all two-phase networks. But it's a problem with two-phase network. Two-phase motors are known for vibration. They have a low torque, they vibrate, and one more problem. Effectiveness. For single phase application, this was sold as a single phase motor. Actually, it's a motor for artificial split network, artificial two-phase network. It's rotor. You see, it's even double. To tamper vibrations, you can see how slots are cut. These diagonal slots are to tamper vibration, but its effectiveness only 30%. 1/3, 2/3 of energy by wasted. They are not effective. Real three-phase motor can give you efficiency 83, 84%, something like this. This one, extremely rare beast. It's for four-phase network. Yeah, this one was for four-phase network. I don't know why, but here it is. Motor for four-phase network. It has 8 coils. Okay. Now Nice question. So, for three-phase network, we need a set of coil with 120 degrees shift. It's all nice and easy, but as you saw, not everything is clear here. For example, question, why nothing happens when I disconnect ground wire? Answer simple. If I voltage system like this, A phase, B phase, C phase voltage, current on active load will have the same structure. And sum of 1, 2, and 3 equals to 0. So ground, in case of symmetrical load, ground current is 0. Near the elevator is a memory plate for Daliva Dobrovolsky. Daliva Dobrovolsky first understood what in three-phase network, ground wire in symmetrical load has a 0 current. So all three can be joined together, all three phases. In four-phase network, you need 4 wires. In two-phase network, you need 4 wires. In three-phase network, you also need 4 wires, but one of them, in case of symmetry, is not loaded. I can, wait one moment. One moment, I can do, come here. Okay, I will substitute phase C with this beauty. It's three times more powerful. Nice? Nice. If I disconnect ground wire, with the ground wire, without, with, without, without. More brutal. I disconnected A phase with ground wire, C phase disconnected without ground wire. In symmetrical mode, where all loads are equal, ground wire redundant. But if loads are not symmetrical, you can see what happens. I can attach voltmeter to B phase, for example. Come on, voltmeter, please. with ground wire 100 volts, without ground wire almost 200. Not a good idea to disconnect ground wire, yeah? Yeah. But now question, can we perform calculus on this? See, in symmetrical mode, if load is symmetric, everything is simple because we have zero ground current, everything looks. What I can separate phase and perform calculus for each phase separate. It looks similar. But in non-symmetrical regimes, and where Doc is digging, where's the biggest problem for me? If I would like to perform a calculus. Do you feel it? No? Simple thing, over here at one. Oh, over here at one. First element. Protected by nice insulators. Let's say A, B, and C phase. And I have full current flows in ground. I will have current here. I will have current here because towers are grounded. And what about other phase? All fine, but they are in proximity. This means that they are magnetically coupled. Yeah. Wires are in proximity, so there will be a magnetic couple. In reality, I need to do something with, at first, a model like this. Self-resistance and self-inductance of protected cable. These are self for A phase. Self for B phase. Self for C phase. A, B, C. Current, current, current. Is it all? No, that's not all. I need to take into account AB magnetic coupling. BC magnetic coupling. AC magnetic coupling. And magnetic coupling three magnetic couplings to between phase and protective wire. Here is network I need to deal with. Easy. Okay, we can account magnetic coupling as a mutual resistance, yeah? We did it. But this network isn't pleasant. It's feasible, but hardly feasible. Mutual couplings make equation system less feasible. It's harder to solve. But this was a simple thing. What about transformers? We need transformers because why? Why we need transformers? Losses. We need to step up voltage for let's say energy transport. Or if we try to distribute at 0.4 kilovolts, we will need wires like this. If you double voltage, your transferable power will quadruple. So higher voltage, higher transfer capability. But customer, we cannot connect wall outlets to 10 kilovolts or 24 kilovolts. We need to step down. So we need transformers. At generation point, we need to rise voltage, use high voltage line to transfer, and go down at customer connection point. And what about transformer? BTV I omitted wire to wire and wire to ground capacitance. For 10 kilovolts they can be omitted. For 1 megavolts, no. Okay, simple thing, transformer. Primary side, secondary side. A1, A2, A1, B2, A1, C2. Hop. A1, B1, A1, C1. You see where the wind goes? B1, C1, A, B, it's free. Here, A2, B2, A2, C2, and
B2, C2.
B2, C2. Free here, plus one set of free. Second one. And third one. 9 primary, secondary. You will have to deal with 3 plus 9 plus 3 mutual inductance. Where to run? Actually, this can be solved, but it's it's hardly feasible. It makes huge system, and it's reasonable only in case you need super high precision. Schematic of real, it was, I saw it. It was there. Schematic for 300 kilowatt line, complete, precise in phase coordinates. It took row of paper, this row of tables, and third one, 2 rows of table in size. It was there. I saw it. I was able to test it with my finger. It takes 2 rows of tables. It is, how to say, it's a dead end. The solution. Idea is, we need to change game field. This game is a bad game. We need to change a game field. And what's the idea of this change? How can we solve it? The idea is to do something to eliminate most of these magnetic couplings. In symmetrical mode, for example, you have phase, 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 and something here. And you have magnetic coupling, magnetic coupling, magnetic coupling. If we are in symmetrical mode, we will see again nice stuff. And some of these influences will be what? If all couplings are symmetrical. 1, 2, 3 equals to 0. And then, what's the idea? In symmetrical mode, when you have this nice voltage or current start, many coupling effects can be emitted. So what's the idea? In general, you have kind of resistance matrix. The main diagonal is ZA, self ZB, self and self. Main diagonal is of self elements, and this will be AB, AC, BA, CA, so on. You understand? This metal resistance. If we can find linear transform, like, let's say, some x in symmetrical space equals to some transfer matrix multiplied by x in phase, here should be original A, B, C phase. If we can find a kind of transform, so for this network would be 0, of course excluding E equals to 0. So if we can find a kind of transformation when non-diagonal elements of resistance matrix would be 0, we can do what? We will have drastically reduce in calculus work and key moment if system is symmetric. If we know what XA, let's say, equals to XB and equals to XC in magnitude, and this angle is always 2/3 pi, we can calculate only one phase. We can operate with single phase network, knowing what other phase can be simply obtained how? By rotation. Amplitudes are equal, so if we have something for A phase, we can easily get, for example, B, how? Just rotate it backwards 120 degrees. It's all on complex plane. We can rotate vectors as we wish. One. I printed one large paper, these two guys. Wilson Long and Mr. Geropoulos, so excuse me, Mr. Geropoulos. 1982, they proved, or they laid a real foundation for this idea. Idea of elimination of non-diagonal elements in resistance matrix by, let's say, imaging our system to new special functional space of symmetrical components. But first, there are set of such techniques. Fortescue, Clark, Wedge-Paul, current power transforms, and also set of no-name transforms. They just exist. As it usual in scientific, first one of such transform found, and later real capital scientific base was laid. So idea, first glimpse of the idea is 1918 by Fortescue. Real applicable published in 1932. Yeah. By Wagner and Evans. So what's the idea? Idea is to substitute real non-symmetric network with a set of symmetrical network, or represented as a sum of symmetrical network. Actually, if you have polyphase network with m phase, you will need m-1 symmetrical polyphase network plus one special for zero for ground wire or zero sequence. Here, for simple three-phase network, we will have two symmetrical three-phase network, A, B, C, 2, 3, this angle also. Symmetrical, ideal symmetrical network called system of direct sequence and marked with the number 1. Direct. Plus also ideal symmetrical network of negative or reverse of negative sequence. It's ideally symmetrical. It's only one moment. It has an opposite phase sequence. It's rotate. If this network will torque your motor clockwise, this will rotate counterclockwise. So it's a generator. It's like a generator with sloped phase or negative rotation direction. These two are three-phase network with angle between phase 120 degrees. For both A equals to B in magnitude equals to C. And network is needed. This is special network to reflect ground current. Here it's called zero sequence network, and here A equals to B equals to C. All phases are equal. zero sequence network. Introduced to reflect ground current. Fortescue transform defines as XA, XB, XC, I don't know, it can be current, it can be voltage, it can be everything, equals to 1/3 1/8 squared 1/8 squared A 1 multiplied by XA phase, XB phase, XC phase. Point. They are complex. All these are complex value. 1 second. Direct sequence, negative sequence, and zero sequence. Why I'm writing inverse transform before? Sorry. One tiny moment. These values, as I wrote, will correspond to phase A of this ideal network. It's important. You can perform calculus for any phase, but if you take as a phase not A, you will need to introduce rotation between coordinates of synchronous machines and coordinates of your network. It's not fatal, but why do we need it? So all this corresponds to A phase of the ideal symmetrical network. And of course question, what's this? What means A? A is a rotation operator, A power yod 2/3 P, or minus 1/2 plus square root from 3 divided by half. Multiplying something by A means, let's say this is X, multiplying by A means rotated forward 120 degrees. Multiplying by A square, this is A square X, means rotation forward 230 degrees. A square is 1 minus square root of 2 by half. Transition matrix, this transfer matrix, in case of Fortescue transform, contains what? Rotations. I knew people who do this transfer simple on paper with the help of ruler and angle scale. For such case I have one, but it's under voltage. No, to prevent from stealing. Yeah, this is nice. Already one important, very important remark. Yes, I draw a nice formula, very nice idea. Let's substitute our non-symmetrical with set of free symmetrical. Real amount of work, this real computation burden will be less because we eliminate not inductance. But there is one very important moment. I need to make a capital remark. This trick, substitution, it's again version of how to say, superposition techniques. This approach, such approach, requires linearity of the network. It can be done only if impedance are constant. In case of non-linear network, nothing will work. If you need exact model of arcs are not linear. If you need a precise account for transformer cores, this will not work. In such case, you need to do a trick. Trick is separation, like I did with DC network of transport. Remember? Transport network. What I did? I separate linear and non-linear part. And non-linear part regulator was represented as controlled current source. Yeah? Here the same thing should be done. Non-linearity should be represented as controlled current or voltage source and put as an external element to the linear network. Or nothing works. In the old style books, you will not find it, because it's done. Such thing can be done real only numerical. Analytical solution, no, it's not possible. It's really impossible. Okay. Bit forward. What's a bit forward? I had, I don't know, faulty network. I substituted with what? With separate network for direct, negative, and zero sequence. Real polyphase network will be substituted with free, I will derive from it free, ideal symmetrical network. My Fortescue transform, okay, I have connection between phase values and values in these ideal networks. I perform some kind of solution. I solved it. So I got voltages for direct, reverse and zero sequence, and I got currents for direct, negative, zero sequence. Now what? They are in space or in the world of ideal elements. How can I get real? I need real currents, real voltage, because I need to program my relay. Why it's all about? I need to put here stands relay, when disconnect line. 1, 2, 5. What should I put in? I need parameters of fault to program my relay when to disconnect. I may need parameters of fault to write a good expertise when customer goes, oh, my equipment died. Well, company is to blame. No, company not to blame, it's your fault. I need parameters of regime, but I need reality. Where my profit, no, I don't see any good from ideal world elements. I need reality. I need to know what will be in reality. This means what I need and backward transform. From this, I need real A, B, C phase voltage, and I need real currents. I need real current. So I need, okay, white current. I need what I need. How it's works. Real faulty network, some parameters XA, XB, XC, with X in sequence is 1/3 transfer matrix X in phase. Calculus, something, let's say, I've solved system of nodal voltage. What I get? I get some direct negative zero sequence elements. I've solved it, I got. Now, where's the back transfer? In phase coordinates, inverse Kierkegaard matrix, Y in sequence, or let's say Y A phase, Y B phase, Y C phase can be found as 1, 1, 1, A square A 1, A square 1 multiplied by Y direct sequence, reverse sequence or negative and zero sequence. Here it's a reverse transform. What a beauty. Cool, great.
That's all?
Okay, this is
That's all?
what? Look how many time I still got on my disposal. Write something. See? All this nice, but there is one little problem. I have net with this decomposition from my original real network. I will get, so for example, I have three-phase system. Let's say I have power line, fault. Yeah. From this point, I will derive three ideal systems. Let's say it's a point M1 and 1. System of direct sequence. System of negative sequence and zero. System of zero sequence. This one negative and this one zero. They all, it's easier for me. They all the system corresponds to a phase of this ideal, not to a phase of real system, but to a phase of ideal system. Now question, how can I need something to connect them together. A, B, C, direct sequence, A, C, B negative sequence, and my ground zero sequence. It's all nice. I need what's behind this plus. How to connect them together? Each of this system will or can be solved with a system of linear equation. There is no problem. I can solve it even with Kirchhoff. I can no problem. I can create free system of Kirchhoff equation for direct sequence, for negative, and for zero sequence. They will give me free system of equation, but they are, how to say, local. For this network, for this, and for this. Free system of equation. But how can I connect them together? I need some kind of coupling. How? And here is important moment of border conditions. How all this can be interconnected. See, I need a common assembly. Here's my idea. A phase. Resistance ZA connected. B phase. Resistance B connected. And this is C phase, and I have a resistance E. Also, neutral resistance present. All this not important. I have something at the point of, this is my point, where each phase has a resistance plus, neutral also has its own resistance. A phase current, B phase current, and C phase current. May show voltage. This is C phase voltage. This marks B phase voltage, and tiny one for A phase voltage. Oh! Such kind of non-symmetry. All different. First, A phase current. This will be C phase current and B phase current. zero sequence current should be A phase plus B plus C divided by 3. Huh? Here E neutral is EA plus AB plus AC, but there is no 3. So it will, I should write, it's a triple current of zero sequence. You saw somewhere this. No? It was somewhere. In electrotechnic basics. Where you saw this? Triple I0.
Star connection.
Yeah, start. Somewhere. It should be in basics of electrotechnics. Huh? Usually it's appear without any sense. Should be. I should avoid this, but it's a fact. I can write a system of equation. Okay. A phase voltage is A plus triple neutral I0. B phase IPZB plus triple neutral resistance and zero sequence current. And C phase voltage is C phase current, C phase resistance plus triple I0. System of equation. I can do what? Apply a Fortescue transform. If I apply a Fortescue transform to this, I will get something like this. OA direct sequence, OA negative sequence, O0 equals to 1/3, 1 A square, 1 A square A, 1, 1, 1, multiplied by OA, OB, OC, or I can write it as O is 1/3 sorry, O sequence, O phase. So what I will write? Voltage, a sequence, 1/3, trigonal matrix, diagonal matrix of resistance, plus Z neutral Kierkegaard matrix, E phase. Here, this one is a matrix ZA, ZB, and ZC. And this one is a ground resistance matrix, like this. Something familiar? No. I can write phase currents as inverse Kierkegaard in symmetry. This will give me very nice Kierkegaard was threefold.
You don't have divided?
Yes.
Are you saying Hindu?
All complex. All these are complex.
Oman has same reason that
Nice formula.
we have
Hey.
divided.
What will you say about this formula? It's a very important and rare beast. You can find it anywhere. Exactly this form, connecting all sequences together as a matrix equation, exists nowhere. Really. Your only particular cases in this, wait 1 second, picture it and I will write it, how to say explode. I can write it explode. At a fault place, A phase direct sequence, A phase negative sequence to 0 equals to 1/3 1 A square 1 A square A 1 1 1 multiplied by ZA ZB ZC multiplied by 1 1 1 A square A 1 A square 1 plus triple 0 0 neutral second bracket equals to direct sequence A negative sequence I 0. Here it is in phase coordinates. This connects sequence currents to sequence voltage. This can be used to create an iterative process for any tie or top kind of non-symmetry. It's applicable if you have a computer and you know how to create iterative process. None of all timer used it. You can find some trace, something. Usually, people use simplified form first found by, I would say, how to find by fathers of this technique, and simplified forms can be derived. This one interesting moment. If you can find for this multiplication, if you can find a substitute where all elements will be real, this can be denoted or represented with the real network. So I call the magic schematics. There are, well, for us are known several so-called magic schematics where one united network can be conducted. First so-called magic schematics is with okay, like this. A, B, C. Very well known schematics where ZP equals to ZC and equals to infinity. So only A phase is connected. For this case, actually, how to say, fathers of this technique, founders, found this solution. In opposite way, they try to write this condition from the network state. And they found this magic schematics. In reality, where B and C are equal, you can really you can always conduct a network for phase E. A. This one, A phase, this one is classics of, you will see it in any book on symmetrical component. And corresponding network is a classics. Is a sequential connection of sequences. So I will need equivalent I will draw equivalent EMF for direct sequence. It's like Thevenin theorem. Equivalent resistance. Here is my connection point and one. What's this? I have a line and a ground fault, let's say it can be fault resistance at a point M. This corresponds to real ground, real earth. It's a common path for direct sequence and one. For the negative sequence, to make it simpler, I will reduce all network to its equivalence, to input resistance. What will show all matter if I connect it at the point where M2 and 2. Equivalent resistance of the zero sequence, so they are connected like this. If RF, I will need to write it triple. Why triple? Everything you put in a ground wire, free currents flow. To reflect it correctly, you need resistance triple. Because this schematics is for only one A phase. Like this, like this, like this. And current flows here will be A phase current of direct sequence. Here is equivalent schematics, also called complex schematics for line to ground fault. It's most easy to calculate. It corresponds to A phase. You need BC, you will need, in simple case, we just rotate. It is not, see, for protection, I assume phase equal. For protection, current of A phase to ground fault, I assume equal to B to fault. If not, if I need to account some differences, I will need go take this nice book. Elektriska sistēma, nesimetriska režīma, matemātiska modelēšana. Mass modeling of non-symmetrical modes of power systems. Find on page 16 are two nice formulas for BNC phase. I knew only one book where they are in, yeah, this one. In that is matrix support. Even on they are too rare, very rare book on non-symmetrical and complex, but they don't see. They wrote on cases for professional, oh, you know it. Of course, no one. One more schematic. What can be next one? Ideal line-to-line form. In case of ideal A, B, C, so I have a fault at the point, and it's kind of this one, BC fault. Exactly, you need to conduct that B should be equal to the C. For such case, this will be your direct sequence equivalent, direct sequence MF, M1, ZB, equivalent of negative sequence. And current here, again, A phase direct sequence. It's a kind of magic, but they should be equal, or this will produce useless result. Line-to-line fault, it's a classic of line-to-line fault. One moment, where's the zero sequence? In such case, since I don't have a ground connection here, no zero sequence is required. No ground current. What's time? Okay, I will continue next time.